Hi, my name is John. I'll be talking about our work on exploring large all-flash storage system with scientific simulation. This is joint work with Junming, Greg, Scott, Norbert, Ronan. Here's a quick outline of the talk. I'll give a very brief overview of the storage system and why is it interesting and why do we do our testing. So then I'll talk about the software tools that we use for testing, followed by some more specifics of the testing measurements and observations. I'll give a brief summary at the very end. What makes our flash storage system interesting is in Perlmutter we have the very first supercomputer with an all-flash file system. And we all know that an individual flash device has higher I/O bandwidth than a typical spinning disk, and it also have a shorter access latency than a spinning disk. Both of these give our flash storage devices a lot of advantages over spinning disks. On this particular Perlmutter system, the peak I/O bandwidth is 5 terabytes per second, which is higher than any other system around. Now, why is it worthwhile to do more measurements? And here is one set of measurements about an individual I/O server on Perlmutter as compared against another system called Cori, which uses a disk-based storage system. The blue bars shows the write bandwidth. What we see here is Perlmutter has 5 to 9 times higher gigabyte per second than Cori, which is what we expect. However, it also shows another set of numbers labeled IOPS, that is shorthand for I/O operations per second. On the first side, what is surprising is Perlmutter system has lower IOPs than Cori. Of course, one of the main reasons is Perlmutter is using rate 6 while Cori was using rate 0. So Perlmutter is trading lower IOPs for more resilience. However, this is one indication, depending on the configuration, we actually get lower performance. So this is one reason why it is worthwhile to do actual measurement. This next shows another set of performance measurements that further indicates why it's worthwhile to actually measure the performance rather than just trust we can get peak performance. So the top left figure shows that the write performance has a broader distribution and it has more likelihood to be lower than the peak performance. More specifically, if we use one storage server, which is called OST in this terminology, OST stands for Object Storage Target. If we use one, there is a 7% chance the performance will be less than 90% of the peak performance. However, if we use 4, the percentage increase to 24%, and if we use 16 OSTs together at the same time, the performance that's less than 90% of the peak increases to 67%. So it's worthwhile to actually measure the performance, because if we're going to put hundreds of this together, we need to know, we cannot just trust it will achieve the peak performance. For our measurements, we're going to need software tools, and I'm going to mention two of them. One is called Adios. This is a very efficient I/O framework. It has many very optimized I/O engines, which means we don't have to do a lot of tuning to get good performance. The second tool we use is called OpenPMD API, and this is because the simulation software we're going to use is relying on this software for I/O performance. I mentioned we don't need too many options for using Adios. However, we are exploring only two of them. They are related to how many subfiles we generate when we run our I/O program. One option is called node aggregation. The other option is called rank aggregation. If we use n compute node, the node aggregation produces one subfile from each compute node, while the rank aggregation refers to the fact that each MPI rank produces its own subfile. And since we use 4n ranks altogether, so it will produce 4n subfiles from this option. So in our tests, we will not only test the node aggregation, but we'll also test rank aggregation. Furthermore, we'll test a number of cluster layout options. The default layout option is called progressive file layout. And here are the parameters for it. I won't read it. The other option we're going to test are specifically setting something called stripe count and stripe size. We're going to be exploring dozens of these combinations. So here's the performance summary. The top right figure shows a gray bar and a red bar, where the gray bar is with the default cluster file layout, and the red bars are from the performance achieved with best combinations of stripe count and stripe size. So the top figure is for load aggregation, the bottom figure is for rank aggregation, and what we notice is that the maximum of y-axis is higher for the rank aggregation. That means in general, rank aggregation achieves higher I/O rate than node aggregation. The other thing to mention from this figure is that the default layout is very competitive against all the combinations of stripe count and stripe size combinations that we are able to explore. Next, we're going to show some more details. This is a set of performance measurements with load aggregation. The different color bars are different combinations of stripe size and stripe count groups, and we are grouping the same stripe size together, or stripe count together. What we see here is, in general, with the node aggregation, if it's possible to set some combination of stripe size and stripe count so that the performance is better than the default. However, we don't seem to have a good handle on what exactly are the values of stripe count and stripe size to use. So further exploration is needed in this case. With the rank aggregation, what we see here is that default always performs better than our manually set stripe count, stripe size combinations. Furthermore, the performance we achieve is about 1.4 terabyte per second. Now, the summary is here. So Perlmutter seems to be configured very well. The reason I say this is the default option is very competitive against the manually set options. However, even with this relatively good performance, we're not able to achieve 5 terabytes per second. So additional work is necessary here. We are doing a lot more testing at the moment, and I promise to show some scientific simulation. So this is a difference. This is a figure shows a number of performance measures with a scientific simulation code called warp-X. The right axis, the vertical axis here is the total end-to-end simulation time. The surprising thing here is because this is a real simulation, so the computation actually takes quite a bit of time. It's possible to completely hide the I/O time using IDOs. Therefore, we are doing further exploration to see how we're going to present the performance of this big file system while we have ways to completely zero it out. So that's why this is the paper itself only shows the benchmark and I/O measurements, not with the actual simulation. Okay, here's the end of my presentation. I'm going to take some questions if there's any from the audience.